Hey guys, Professor Hildebrandt here. I'm going to do this a little different than the last chapter. First, I'm going to just do a full content lecture on chapter 10 where I just work through the examples that were outlined in the textbook. And then I'll do a separate video where I work a few additional problems on hypothesis testing. Okay. So really all we're trying to do in this chapter is we're looking at a new procedure that tries to help us measure the validity of a statement that we've made about a population. So, if we say the mean is X, we're trying to see how accurate that is. And we can't exactly prove it to be true, but we can be more or less certain, okay, that it's actually representative of the population. And I'm going to go kind of quickly through the first few slides because it's more like definitions and outlining the steps, and then I'll spend some more time doing some examples here. So just definitions here. Hypothesis testing, it begins with the hypothesis statement. So it's a statement about some parameter of our population. So maybe the mean speed of automobiles on the turnpike is 68 miles per hour, or the mean cost to remodel a kitchen in Florida is $20,000. And so again, we're going to use this hypothesis testing to see what we can say about this. Hypothesis testing is used a lot. Okay, it's used in a lot of our sciences, and so this is not just limited to like a business statistics class. So we have a 6-step process here. And I'll go through each of these a little bit more in detail. Again, it's really important to note that hypothesis testing in statistics does not provide absolute proof that something is true. Okay, that's not the goal here. But if we carefully go through the 6 steps as they're outlined, then we could at least provide, kind of like what they're looking for in our court system, proof beyond a reasonable doubt. Okay, that something either is true or is probably not true. Okay, so the first step is to state what we call the null hypothesis, H sub 0, and then the alternate hypothesis, H sub 1. And so the null hypothesis is that statement that we're making about the population's parameter that we're then going to test. And the important thing about the null hypothesis is it always includes the equal sign. So it'll either be H sub 0 equals something. So if we're talking about like the population mean is 200 and we're trying to see, can we say yes to that? So then our H sub 0 would equal 200. Okay. Or if it's a range, then we would use, if it's going to be greater than, it'd be greater than and equal to, or less than and equal to, okay, for the null hypothesis. The alternate hypothesis is different because it's a statement that, if accepted, the sample data does not provide sufficient evidence. And so it's the opposite, and it's never going to include the equal sign. And so we have 3 options. Again, if I said that our null hypothesis was a mean of 200, then the alternate hypothesis is that it does not equal. And so we'd use the does not equal sign, 200. Or it could be less than or greater than if we're looking for, again, a range. And so when we do this testing, we either reject the null hypothesis or we fail to reject the null hypothesis. But again, failing to reject the null hypothesis does not prove that it's true. It just means we have failed to disprove it, which can be kind of confusing, I know. Okay, so then the second step in our process here is we have to select what we call the level of significance. We use the lowercase Greek letter alpha for this. And the level of significance is just the probability of rejecting that null hypothesis when it is true. So it's called the level of risk. And there's not one level of significance that's applied to all tests. whoever's conducting the research needs to decide on the level of significance before formulating, like before going any further in the testing process. And so these are just some typical ones that we use. 0.05 is typically used for consumer research projects. So we call that a 5% level of significance. 0.01 for quality assurance. So you can see it's a smaller range, right? We want to be more accurate here. So 1% level, whereas political polling is at a 10% level of significance. There is a possibility that we'll have some errors in our hypothesis testing. And so we have two errors here. A type 1 error is when we reject the null hypothesis, but it was actually true. Okay, so that's one mistake that we could make. And that's where we use that Greek letter alpha to designate a type 1 error. And then a type 2 error is the Greek letter beta, and that is not rejecting. So we fail to reject the null hypothesis, but it is actually false. And I'm just not going to spend too much time about these, but just wanted you to know that we can have errors in this, and this is what they're called. Step 3, we have to select the test statistic. So this is going back to previous chapters. If we know the standard deviation of our population, then we'll use the Z statistic. That's what we'll compute. And we're going to use that same formula right here, guys. That, again, we've been using in previous chapters. So we take our sample mean, we subtract the population mean, and then we divide by that error that we had, right, in chapter 9, which is, again, is equal to the standard deviation divided by the square root of our sample size. And so we'll calculate a Z value here. If we don't know, right, this is what we got into with chapter 9, if we don't know our population standard deviation, then that's where we're going to have to use our T value as the test statistic. And I'll show you that formula in an example here at the end of the chapter. And then we'll formulate what we call the decision rule. So a statement of specific conditions where we do reject the null hypothesis and the conditions under which we fail to reject the null hypothesis. And so this is going to be a region under our curve, right? So we're still working with that normal distribution that we've seen now in several chapters. And this is called the critical value. The dividing point between the region where the null hypothesis is rejected and the region where it is not rejected. And so on this next slide here, I'm going to show you a quick example here of the critical value. And so maybe we had a sampling distribution and we had the Z statistic here. Our alpha was 0.05. We're doing what's called a one-tailed test. I'll talk about that in a second. And so the critical value here is that 1.645. It separates the region from where the null hypothesis is rejected. That's this, we call this tail over here. And then this larger area under the curve here to the left of 1.645 is the area where we would fail to reject, okay, the null hypothesis. So that's what we mean by critical value. Once we've done all of that, we're going to make a decision. So we'll look at a sample. We'll compute the value of our sample mean, let's say, and then we're going to test it. We're going to see, does that test statistic, how does it compare to the critical value, okay? And then we'll make that decision regarding whether we reject the null hypothesis or fail to reject the null hypothesis. And so, and then we interpret our results. What can we say or report back out based on our hypothesis test? And so if the results of the test let's say we result in a decision not to reject the null hypothesis, then we could say, well, based on our sample data, the difference between the sample mean and the hypothesized population mean was not large enough to reject the null hypothesis. On the other hand, if our results are that we do reject the null hypothesis, then we have disproved the null hypothesis with that stated probability and then the type 1 error, that alpha, okay? So there's still a small probability that the decision to reject was an error due to random sampling. All right. So here's just showing some examples, the differences between the one-tailed and a two-tailed test. If we're using the null hypothesis equals this value and the alternate hypothesis does not equal, then we use a two-tailed test. And so you can see here in this middle one, we've taken the significance of 0.05 and divided it in two. And so we have 0.025 here in the tail on the left and 0.025 here on the right. If we're saying that the null hypothesis is greater than and the alternative is less than, then we would have a left-sided one-tailed test. And again, the significance here would be 0.05. And so that's all on the left. If instead the region of rejection is a greater than, see how the alternative here on this third one here is greater than 453, then it's a right-sided one-tailed test, okay? So let's work through some examples now. First, we're going to do a two-tailed test example with our standard deviation being known. And so, you can read all this. I'll let y'all do that. But we've got normal distribution. We find that the mean of the population is 200, and the standard deviation is 16. And this is for, I think, the production of desk, okay, at a plant, weekly production. But they've had some new production methods have been introduced, and they want to see if there's been a change in weekly production. And so we're trying to figure out, is the mean number of desks now produced different from that original population average of 200? And we're looking at this at the 0.01 significance level. And so this is a two-tailed test because our alternative hypothesis does not state a direction, right? Our null hypothesis is that the mean is still 200 desks, and the alternative hypothesis is that the mean is not 200 desks. Sorry, y'all. I had a 2-year-old run in here real quick. The level of significance here was established for us, so our alpha here is 0.01, and because we know the standard deviation of our population, then our test statistic is going to be the z-value. And so, again, here is the formula that we're going to use to calculate that z-value. All right, so let's look at the area here under the curve and try to pull this all together. So to formulate our decision rule, we have to determine that critical value of z. Now, since this is a two-tailed test and our level of significance is 0.01, then we're going to divide that in half. And so we'll have 0.005 and 0.005 in the right-sided tail and the left-sided tail. And so those regions here on the two ends, those are our regions of rejection. And to find the critical value, we are actually going to use the t-distribution table in Appendix B5. And so you might want to pop over to your textbook really quick and look at that. And you're going to go to the top margin called level of significance for two-tailed test, alpha, and then find the column for 0.01 and move to the last row labeled infinity, and the z-value there for that cell is 2.576. And so our critical values is a positive 2.576 and a negative 2.576. And so if the sample statistic that we get falls in between those two values, then the null hypothesis would not be rejected. So let's see here. So then we're going to take an actual sample and calculate the test statistic. And so they do the mean number of deaths produced last year. During 50 weeks, the plant was shut down for 2 for vacation, was found to be 203.5. And we already knew the standard deviation for our population was 16 deaths per week. So we are going to compute our Z. So we take that 203.5, we subtract what we thought was the population mean of 200. We divide by 16 divided by our sample here was 50 weeks. So the square root of 50. And we get a Z value of 1.547. And if we look back then, well, it's not going to let me. But if we were to look back under our curve, we would see that 1.547 does not fall in the rejection region, right? We would have needed to be, it was greater than like 2.5 something. And so we decide not to reject our null hypothesis. So because we didn't reject the null hypothesis, we have failed to show that the population mean has changed from 200. So what would we tell the vice president? We would say, okay, Vice President, the sample information fails to indicate that the new production methods resulted in a change in the 200 deaths per week production rate. However, we didn't, absolutely prove that the assembly rate is still 200 per week. We just failed to disprove it, which is, again, not the same thing as proving it to be true. But either way, the VP is probably not going to be too happy because we probably spent a lot of time and money putting in these new production methods, and we have not proven that the assembly rate is not still 200. It probably is. So, let's compare this to what a one-tailed test example would look like. So instead of wanting to know if there'd been a change in the mean number of deaths produced, what if our VP wanted to know if there had just been an increase in the number? And so, could we conclude that based on the improved production methods, the mean number of deaths in the last 50 weeks was more than 200? Okay. And so again, our two-tailed test was, hey, it's still 200, or hey, it's not. And now we're going to say, for the null hypothesis, are we producing 200 or fewer deaths, or are we assembling more than 200? And the critical value here for a one-tailed test will be different from the two-tailed test, even at the same significance level, because remember, in the two-tailed test, we split the significance level in half, and we put half in the left side and half in the right, or they call them the lower and upper regions, upper tails. And for a one-tailed test, all of the rejection region is on one side. And in this case, since our alternative is greater than 200, the one-tailed side is going to be on the right, the upper tail. So again, we're going to use Appendix B5, and we'll move to the top heading called Level of Significance Alpha. Select the column with an alpha of 0.01, and then we'll move to the last row, which is labeled infinity, and we find our Z value here, or our critical value, to be 2.326. And so you can see now that the differences, so here's the side-by-sides in terms of the distributions, right? This was the one we just worked with the two-tailed test, and then here's what it would look like with the one-tailed test. The next part in the chapter talks about the p-value, and so this is the probability of observing a sample value, or the probability that the value of this test statistic of our sample is as extreme as the value computed, if our null hypothesis is true. And if we have a very, very small value, like 0.001, then there's little likelihood that the null hypothesis is true. On the other hand, if we had a p-value that's larger, like 0.2033, then that would mean that our null hypothesis is not rejected, and there's little likelihood that that is false, that we have an error there. And so you can see here on the slide, right, we've got some more. If the p-value is smaller than the significance level, we're going to reject the null. If it's larger than alpha, then our null hypothesis, we fail to reject it, okay? And, how does this help? Well, if our p-value was 0.1, we have some evidence that the null hypothesis is not true. But once that lowers to 0.05, we say we have strong evidence that it's not true. At 0.01, we have very strong evidence. And finally, at a level of 0.001 for our p-value, then we're basically saying, yeah, there's no way. This is extremely strong evidence that our null hypothesis is simply not true. So earlier we were talking about the desk production. We calculated that Z to be 1.547, and we did not reject the null hypothesis. So let's just round that up, that Z value, to 2 decimal places of 1.55. Using your Z table, find the probability of finding a Z of 1.55, and you would get an area of 0.4394 from your Z chart, your scores chart there. Remembering that 0.5 is the area on each side. We subtract from 0.5, and the area here would be 0.0606. But since it's a two-tailed test, we have 2 of those orange areas you see down here under the curve, so it'd be equal to 0.1212. And so the probability here of finding a sample mean greater than 203.5 desks when the population mean was 200 desks is again 0.1212, or about 12%. And since the p-value of 0.1212 is greater than our significance level here of 0.01, so our null hypothesis is not rejected. Okay, the last part here that we're going to cover in this chapter is hypothesis testing when we do not know our standard deviation, and it's really the same process. The only difference is, remember this formula from our last chapter, we introduced that new thing called the t-distribution. So we just have a different test statistic for our sample because we don't know the population's standard deviation. And so this is just a review down here of what a t-distribution is like. And so we've got an insurance company, and they find the mean cost to process a claim is $60. And they look at their industry comps, and they find this to be larger than most other insurance companies. And so they constitute some cost-cutting measures. And then they're going to try to evaluate, hey, did this actually work? Were we able to lower our cost? So they take a random sample of 26 claims that have been processed last month, and the cost of each is down here. And you can see some were less than 60, right? Some were greater than 60. So first, step 1, again, same 6-step process. State the null hypothesis and the alternate hypothesis. So our null hypothesis is that the mean is either greater than or equal to 60, in which case, we're doing worse in terms of our cost cutting. And then the alternative is that it's less than 60. So we're going to use a level of significance here again of 0.01. And for our test statistic, we can't use a Z because we don't know the population standard deviation. So we're going to use a T. Okay. And then we're going to formulate our decision rule. And so again, we're going to use Appendix B5. And this is a one-tailed test. So we're going to find the row at the top labeled level of significance for a one-tailed test alpha, and locate the column with 0.01. You can see it highlighted here. And then for our degrees of freedom, right, the n-1. And so our sample size was 26. So 26 minus 1 is 25. So this is the row that's highlighted. And where those two meet, that is going to be our t value. And so the value here is 2.485. And since this is a left-held test, because our rejection area is here, then it'll be a negative 2.485. And so then we take our sample and make the decision. So here is the formula again that we're going to use. And so for our sample, the sample mean was $56.42. Okay. Our population mean, remember, was 60. We're dividing by our sample standard deviation and then the square root of the sample size. And so we get a t value of minus 1.82. And so you can see where that would lie under the curve. And so the decision is we do not reject the null hypothesis, because remember, the rejection region is this tiny little area over here on the lower left side. Okay. And so because that 1.82 is in the region to the right of the critical value, the null hypothesis is not rejected at the 0.01 significance level. We have not disproved the null hypothesis. So what would we say back to management? Well, we would say the test results do not allow the claims manager to conclude that the cost-cutting measures have actually been effective. Again, probably not something they want to hear, but this is how businesses really do use statistics. Okay, another video coming up soon where I work some more examples and hopefully help you guys understand this a bit better.